GO-LoW is a new kind of telescope that will allow us to view the sky at very long radio wavelengths. These are waves that are 15 meters to several kilometers in length. Because the waves are so long, we need a really big telescope to make detailed images of the sky. GO-LoW is therefore a constellation telescope made up of many thousands of spacecraft that work together semi-autonomously with limited input from Earth. GO-LoW will allow humans to see the universe in a new light, opening up one of the very last frontiers in the electromagnetic spectrum. With this new view, we'll learn about the magnetic fields of exoplanets in the local solar neighborhood, improve our understanding of how the early universe evolved from the Big Bang to the stars and galaxies we see today, and we'll map out the stuff between the stars and our own galaxy in unprecedented detail. The semi-autonomous constellation architecture we'll develop for GO-LoW will have applications to other science goals, from heliophysics to planetary science and beyond. This new mission paradigm has big benefits, including massive redundancy, the ability to upgrade the constellation with new tech, and reconfigurability as science goals change.
Humans have built telescopes on the ground and in space that can see the universe across nearly the entire electromagnetic spectrum. Gamma rays and X-rays, through visible light and infrared, and even to centimeter radio waves. But we've never seen the sky at the longest radio waves, longer than about 10 to 15 meters or 15 to 20 megahertz in frequency. At these long wavelengths, Earth's ionosphere doesn't allow radio waves to pass through. So the question is, why haven't we built a space telescope to explore this part of the spectrum? It's because a telescope must be many wavelengths across to provide resolution. So a telescope that observes waves tens of meters to kilometers long must be hundreds of meters to many kilometers across. GO-LoW is an array of spacecraft spanning thousands of kilometers. With GO-LoW, we'll finally be able to see the low-frequency sky in fine detail. And what will we see? Exoplanets in the solar neighborhood, blinking on and off with radio aurora from their magnetic fields, interacting with stellar winds like fireflies in the dark. These radio aurora carry important information about their planets, whether or not the planet has a magnetic field, how strong it is, how fast the planet is rotating, and even hints about what's inside each planet. Studying exoplanet radio aurora and the magnetic fields that they trace is an important piece of the habitability puzzle, and it's a key science goal for GO-LoW.
Because the low-frequency part of the spectrum is so unexplored, there's exciting science that can be done at a range of constellation sizes. A small precursor to GO-LoW, with about 10 nodes, would let us explore the radio soundscape of our own solar system, including tracking solar coronal mass ejections and studying their impact on other solar system planets. It would also enable us to map out our local galactic neighborhood below 10 megahertz with better resolution than ever before. As constellation size increases to 100 spacecraft, both sensitivity and angular resolution will improve. At this size, the constellation could study Uranus and Neptune at the outer edge of our solar system and begin to make discoveries about the early universe during the cosmic dark ages. And as the constellation continues to grow to 1,000 nodes and beyond, the science grows too. We'll make finely detailed maps of the sky. And at GO-LoW's full size, we could finally learn about the magnetic fields of our neighboring exoplanets via their auroral radio emission.
The GO-LoW concept takes advantage of next-generation launch vehicles with large diameter fairings like SpaceX's Starship. Several launch vehicles filled with thousands of GO-LoW spacecraft will be sent up to LEO, and once there, they'll be refueled by previously launched propellant tankers before journeying on to an Earth-Sun Lagrange point like L4. Earth-Sun L4 forms an equilateral triangle with both the Earth and the Sun and is a very gravitationally stable point in space, requiring minimal propellant once the constellation gets there. And the large distance from the Earth, 1 AU, or about 93 million miles, means less radio frequency interference, which can otherwise threaten to overwhelm GO-LoW's sensitive measurements.
The GO-LoW constellation will have a hierarchical architecture consisting of many small listener nodes and a smaller number of larger communication and computation nodes. The listener nodes are small, relatively simple 3U CubeSats. Their size is roughly like a loaf of bread. They collect data with their vector sensor antennas, store it in memory, and periodically send it to their CCN via a radio link. CCNs are mini-fridge-sized spacecraft which collect and compress data from multiple LNs. They are equipped with laser communication terminals for sending large amounts of data back to Earth, and we expect each CCN to keep track of around 100 LNs. The CCN will keep track of the positions of the LNs in their neighborhood, collect and reduce LN data, and then transmit that reduced data back to Earth. Final correlation and imaging or other data processing will be done back on Earth where computational resources are plentiful.
In Phase 2, we'll focus on developing the autonomous operations architecture needed to realize GO-LoW's ambitious science objectives. In Phase 1, we learned that GO-LoW's key innovation isn't a specific technology or component, but rather a complex system of systems working together to achieve unprecedented results. Our goal in this next phase of the project is to demonstrate the complex autonomous interactions between GO-LoW's many spacecraft and show that the concept can scale effectively out to 100,000 nodes. To do this, we'll build a multi-agent simulation of the constellation where each spacecraft will be modeled as an intelligent entity that interacts with other spacecraft as well as its environment. The simulation will demonstrate how the constellation will receive high-level mission instructions from Earth and translate those detailed spacecraft-level planning via distributed decision-making. The constellation will be shown to work together autonomously to produce simulated science data that can be sent back to Earth.
The constellation is deployed into 3 nearly orthogonal planes. The satellites execute a regimented pinwheeling motion that allows for straightforward traffic management along the lines of intersection. And they can be set out so the satellites can stably and predictably take turns passing through those lines. As we zoom out, we see the constellation centered around L4 in the context of Earth's orbit around the Sun. Note the geometry and how the orientation of the planes follows Earth's orbit. This configuration exposes a full cross-section, ideal for beamforming to all directions in the sky at all times. And once at the Lagrange point, deployment costs are modest, no more than 1 meter per second of delta V per satellite, and fuel requirements for constellation stability are also modest, estimated to be less than about 2 meters per second per year per satellite.
During Phase 2, we'll also be simulating the science we expect from GO-LoW in more detail. For example, we've taken a simulated map of the sky at 1 megahertz and predicted how GO-LoW will see it at different constellation sizes. The detail in the map increases as we go from a single spacecraft to 4 to 10 to 100 and so forth. We are going to link simulations like this with the multi-agent autonomy simulation as well as the orbital modeling to obtain an end-to-end performance assessment. Developing a calibration architecture will be another key task on the science side. We'll develop roadmaps for both the science and the technology needed for GO-LoW to be successful. For the science roadmap, we'll look at which constellation configurations will be best for a range of science cases and also dig into the modeling and theory that will be needed to interpret data from this powerful telescope. And for the technology roadmap, we'll continue to refine the key technology requirements that will make GO-LoW possible, particularly in the domains of laser communication, computing and autonomy, and network architectures.
We're excited to continue developing the GO-LoW concept with an expanded team in Phase 2. We are grateful to the NIAC program for continuing to support this work.